In this lecture, we're going to talk about surface area and how to compute surface areas of surfaces. So there's a recipe that I will write down first, and then we'll do some examples. So to find the surface area, okay, of a surface, say S, first we parametrize. So for example, suppose you have a parametrization from a rectangle AB cross CD into R3. Now, not all parametrizations start with a domain of a rectangle, but uh, we can get into those a little bit later. And write, okay, t in terms of its coordinates, t of uv equals x of uv, y of uv, and then z of uv. So once we have this vectorial representation of the surface area, we can define some so-called tangent vectors. Define tangent vectors, right? Tu equals dx du, dy du, dz du. So essentially taking all the coordinates here and differentiating by u, and then tv is dx dv, dy dv, and dz dv. Now, as a matter of notation, sometimes we write xu, yu, zu, and xv, yv, zv to mean partial derivatives. Now what we're going to do is we're going to take the cross product, which we'll review in the course of this lecture, tu cross tv, and then consider its norm. Okay, calculate its norm, tu cross tv. Now, these vectors here, and this expression, tu cross tv, is a function of u's and v's, and we define the surface area of S to be, the surface area is the integral from C to D, the integral from A to B, that's my rectangle, of tu cross tv du dv. And again, the integral on the inside refers to the u, and the integral on the outside refers to the v. So integrals are done inside out. So we're going to first do an example. Let's look at example 1. So consider a cylinder, okay, of radius a and height h. Now, the cylinder looks like this, right? What we're going to do is we're only going to look at the surface area of the side. We're not going to include the bottom, right? So the top and the bottom, not included. We can include them at the very end, right? And this is the side, and we're really interested in the side. So just as a check, right? The way that you compute the surface area of the side of a rectangle, of a cylinder, is that you cut it along the height, and then you unfurl it until you get a rectangle. Now the rectangle has height h, and the width of the rectangle was the original circumference of the circle, which is 2 pi r, or in this case, 2 pi a. So the surface area should be 2 pi ah. And then we'll compute it using the surface integral technique and make sure that we get the same result. Now, place the cylinder in 3D axes. So here we'll have the x-axis, y-axis, z-axis, and then we're going to place the cylinder right here, sitting on top of the xy plane, okay? And its radius is a and its height is h. Now, how do we parametrize this? One of our variables is going to be theta, and the other is h. So we will use parameters theta and h. All right, so we're going to take theta between 0 and 2 pi, and we're going to take my height, which I will call a u, a different letter. Well, I guess maybe my parameter should be theta and u. And then this goes from 0 to h, and I embed that into R3. And then, so I could either write this, okay, and then what is my parametrization? T theta u is equal to a cosine theta, a sine theta, and then u for the z-axis. So this describes the circular part, and this describes the vertical part. All right, now we have t theta u. Let's compute the tangent vectors. T theta is minus a sine theta, a cosine theta, 0, and tu is equal to 0, 0, 1. Now let's compute the cross product, t theta cross tu, and that will be I j k minus a cosine theta, a hold on, that's not right. A minus a sine theta, a cosine theta, 0, 0, 0, 1. Now to compute the cross product, we look at the I coordinate. The I coordinate depends on this minor, which is a cosine, gives you an a cosine theta. The J coordinate depends on this minor, which is, if you take the determinant, it's minus a sine theta, but there's an inherent minus sign in the J coordinate, so it becomes a sine theta. And the K coordinate involves that minor, and the determinant of that is 0. And now we take the norm, which is t theta cross tu, and norm is the square root, and then I'm going to square each of these terms. I don't have to square the 0. And so we see we get a squared cosine squared theta plus a squared sine squared theta, right? And I could factor out an a squared cosine theta plus sine squared theta. Well, cosine squared theta plus sine squared theta is 1, so eventually you'll just get a. So the surface area equals the integral from 0 to 2 pi, 0 to h, of t theta cross tu, which is a, du d theta. Now notice that the integrand has no u's and thetas, so all you get is a times, and if you don't have any u's, then what you have is the top coordinate minus the bottom coordinate, or the top endpoint minus the bottom endpoint. And for the theta, the same thing, 2 pi minus 0. So I get 2 pi ah as expected. All right, so now let's consider a second example. Let's consider the cone, okay, given by z equals 2 square root of x squared plus y squared below the plane z equals 3. So geometrically, what's going on here is that I have the xyz plane, and I have a cone given by this formula right here. Now this cone goes on forever, except that we have decided to chop it off at z equals 3. Z equals 3. Now notice that they intersect in a circle right here. And so to find that circle, we're going to have to set the two equations equal to each other. So to find the intersecting circle, we write 2 square root of x squared plus y squared equals 3. So x squared plus y squared, okay, is equal to 3 over 2 squared, or 9 over 4. And so this is a circle of radius 3 over 2. What we do with this circle is that we transport it down here into the xy plane as like a shadow, and the parameters will come from that circle on the bottom. So now we're going to consider the following. We're going to since we're dealing with a circular region, we want to let ourselves use polar coordinates. So let x equals r cosine theta, y equals r sine theta. Now, what is z? Z is 2 times the square root of x squared plus y squared. So that's 2 times the square root of r squared cosine square theta plus r squared sine square theta. Right, you can factor it out in r squared, leaving a cosine squared plus sine squared, which is 1. And then the square root of r squared is just r, so I get 2r. So our parametrization is the following, right? T of r theta is equal to r cosine theta, r sine theta, and then 2r. Now, what does r go from? So this is a circle of radius 3 halves, so the r goes from 0 to 3 halves, and the theta goes from 0 to 2 pi, it's a full circle, and this goes into r3, so that is the precise parametrization of the cone. Now let's compute our tangent vectors. TR is cosine theta, sine theta 2, and T theta is minus r sine theta, r cosine theta 0. So let's compute TR cross T theta, ijk, cosine theta, sine theta 2, negative r sine theta, r cosine theta 0. So let's take a look at the I-coordinate. The I-coordinate relies on this guy right here. The determinant is minus 2 r cosine theta. The J-coordinate is about that. The determinant is a 0 minus 2r sine theta, so positive 2r sine theta, but the J term has a minus sign attached to it, so it's minus 2r sine theta. And finally, the K term is based on this square right here. This is r cosine square theta plus r sine square theta. So but you see that this guy you can factor out an r, and you get something that's equal to 1 left over. So this is minus 2r cosine theta minus 2r sine theta, and just plain old r at the end. So our norm is given by tr cross t theta equals square root of, let me just get rid of the negative sign since we're squaring, square plus 2r sine theta squared plus r squared. So I get a 4r squared cosine square theta plus 4r squared sine square theta plus r squared. Now notice if I combine, like I can factor out a 4r squared out of this. But what remains is just equal to 1, okay, plus r squared. So this guy is just 1. And then I have 4r squared plus r squared, which is 5r squared. So the square root of 5r squared equals the square root of 5 times r. So let's compute the integral from, so the surface area equals the integral from 0 to 2 pi, 0 to 3 halves of tr cross t theta, which is root 5r, okay, dr d theta. Now, let's think about what this is. Notice that there are no thetas in the integrand. So I just have a 2 pi that drops out of this integral, 2 pi minus 0. I have a root 5, and then I want to integrate r squared over 2, 3 halves to 0. I have a little cancellation there. Pi root 5, 9 over 4, which is 9 pi root 5 over 4. And that is the surface area. All right, let's do one more example, and then we'll get into something slightly theoretic, just how we got this formula in the first place. So here's example 3. Similar to the last one, compute the surface area of the paraboloid, okay, given by z equals 2x squared plus 2y squared, okay, under the plane z equals 5. So very much like the question about the cone, we have a paraboloid. This guy should go on forever, but we cap it off at the plane z equals 5. And again, we get a circle on the top. To find the intersecting circle, we set these equal to each other. To find the intersecting circle, right, set 2x squared plus 2y squared equals 5. Let's divide by 2, x squared plus y squared equals 5 halves. So this is a circle, a radius root 5 over 2. So again, we take the shadow right here. Okay? My parameters will describe that circle on the bottom. Now we're going to let x equals, okay, so let x equal r cosine theta, y equals r sine theta. And here z is 2x squared plus 2y squared, which is 2r squared cosine square theta plus 2r squared sine square theta. I factor out the 2r squared, and then there's just 1 left. So our parametrization looks like t of r theta is r cosine theta, r sine theta, 2r squared. Okay. Notice that we have an r squared here instead of an r previously. My r goes from 0 to root 5 over 2, and my theta goes from 0 to 2 pi. Let's compute our TR. TR is cosine theta, sine theta, or r. P theta is negative r sine theta, r cosine theta, 0. TR cross T theta is, okay, so we're going to look at this square. Oh, I guess I should write out the entire thing. IJK cosine theta, sine theta, for r, minus r sine theta, r cosine theta, 0. So the first coordinate depends on this square. If you take the determinant of it, you get a minus 4r squared cosine theta. The j term is here, right? I have a negative, 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 three negatives, a negative 4r squared sine theta. And here at the end, I have an r cosine square theta plus r sine square theta, right? And that guy is just r. Just factor out r, and then the rest is 1. So I just get r there. So let's compute tr cross t theta in norm. I have the square root of 4r squared cosine square theta squared plus 4r squared sine square. No, there's no square there's no square here. It's just 4r squared sine theta, okay, squared plus r squared. This is 16r to the fourth cosine square theta plus 16r to the fourth sine squared theta plus r squared. Now I can factor out a 16r to the fourth out of that. The rest is 1. So I get a 16r to the fourth plus r squared. Now I can factor out an r squared, 16r squared plus 1. And then I can bring the r squared out of the square root, giving me r times 16r squared plus 1. So my surface area is the integral from 0 to 2 pi, the integral from 0 to root 5 over 2, times r square root of 16r squared plus 1 dr d theta. No thetas in the integrand, so I just get a 2 pi here. Now, the standard way of integrating this is by u substitution, u equals 16r squared plus 1. But you can do it faster just by sort of looking at it. This is 16r squared plus 1 to the 1/2 times an r. So when I anti-differentiate it, right, if I have u equals 16r r squared plus 1, then du, right, du is 32r, right, dr. So I have an r, right? I have an r here. I just don't have the 32. So this is what I'm going to do. I'm going to treat this as the power rule, 3/2 multiplied by 2/3. But my du is going to require a 1 over 32 here, okay, between 0 and root 5 over 2. You can do the u substitution out on your own if you'd like. So this becomes a pi over 24. And then let's plug in the 5/2. I get 16 times 5/2. I've squared the square root plus 1 to the 3/2 minus, well, when you stick in r to 0, r equals 0, I just get a 1 there. So I just get a 1. And here we have pi over 24. And then this becomes 41 to the 3/2 minus 1. If you don't like fractional exponents, you can write 41 root 41 minus 1. So let's talk about the reason for this formula, right? Why do we have this formula? So what we want to do is we want to consider the parameter space, right? So let's just take the example where something is a square. Okay. So this is AB and this is CD, and by crossing it, you get a rectangle. what we're going to do is we're going to take lots of, like, let's just break this up into n slices here, and then n slices here. And I want to see what happens to each of these guys under the parametrization. Now remember that what we have is we have a surface, and this is the map T. And what's happening is that when you map these vertical and horizontal lines, they become curved lines on the surface. So you might have something that looks like this. And my job is to compute the surface area of each of these little pieces that kind of look like curved parallelograms and add them together. So let me write some of this down. Okay. So break apart AB cross CD into small squares. Okay. And find out how to compute, right, the surface area of the small, I'm going to call it a, um, a bent parallelogram, right? A bent parallelogram sorts, right? Um, of the corresponding to the square, okay? Corresponding to each. Oh, it's not really a square, it's a little rectangle. Each little rectangle. Yeah, these aren't necessarily squares. These are rectangles. Right. Okay, so let's take a look at what's going on here. Suppose I take a little a square here, or a rectangle. I keep saying, maybe I should just draw it as a rectangle to remind myself it's a rectangle. And suppose this is labeled in the following way. This is UI, VI, this point right here. And then UI plus 1, VI. Here is UI, VI plus 1. And here is UI plus 1, VI plus 1. And what's going to happen is that T is going to map this to a curved or a bent parallelogram like this. And here is T of UI VI, T of UI plus 1 VI, T of UI plus 1 V of I plus 1. Okay. And this corner, let's draw this a little bit more angularly, right? And this corner right here is T of UI VI plus 1. Now, I'm interested in this vector right. Let's take a look at this vector right here and this vector right here. Okay. So one vector, this vector, I don't know, let's call it A, and let's call this B for now. Oh, I already used A and B for something else. Let's call this W1 and W2. How's that? Now, W1 is equal to the final point, the final endpoint minus this endpoint right here, and W2 is equal to UI VI plus 1 minus T of UI VI. Now, what we're going to use here is a sort of a version of the mean value theorem, okay? A version of the mean value theorem. So what does the mean value theorem say? It says that if F, okay, is differentiable on the interior of a closed interval and continuous on the entire interval, then f of b minus f of a is equal to f prime of c times b minus a, right? For some c between a and b. Now, if AB is a very small interval, okay, then the thing is that A is very going to be, so as C is in AB, right? Then, A is sort of close to C. And if F is nice enough, doesn't wiggle around too much, then f of b minus f of a is going to be approximately equal to f prime of a, right? I'm just going to replace a c with an a times b minus a. So I'm going to apply this result up to here. So what's going on here? Here I have two coordinates, but we're stabilizing. This v is the same, so we're not going to worry about that. So this is essentially my a, and this is essentially my b. So this is approximately equal to, right? Oops. Okay. Tu, which is the derivative in u of ui vi, right? So that's this piece right here, the derivative, times ui plus 1 minus ui, and we're going to call this tu of ui vi times delta u. And this is approximately tv, because the v's are changing, of ui vi vi plus 1 minus vi, which is equal to t v of ui vi times delta v. So these tu's and tv's are taking over the role of this f prime. And so we have this these kind of approximations. Now, the second piece of information that we need to use is that now if W1 and W2 are vectors, okay, then what does W1 cross W2 in norm equal to? Well, it turns out that if I have two vectors W1 and W2, okay, then they form a parallelogram. And the area of the parallelogram is precisely equal to this quantity right here. Right, so this is the area of the parallelogram, okay, spanned or created by W1 and W2. So let's go back to our picture. We have a vector here and a vector here, right? So remember that we have a little patch, right? So let's just take this patch and blow it up. So I have this patch right here. And remember that this vector right here, okay, was called W1. And this one right here is W2. Now, this shape is not a perfect parallelogram, but when these vectors are very, very small, then it's approximately equal to a parallelogram. And so we have to make the parallelograms smaller and smaller and smaller. So the area of each piece of the surface is W1 cross W2 in norm. But let's remind ourselves what that is, right? W1 is Tu delta U, right? So it's Tu, I guess I can write Ui Vi delta U cross TV UI VI delta V. And I could rewrite this. I can, um, uh, because the cross product has nice scaling properties, I can actually remove this right from here, UI VI, okay, and then pull these out right here. Right. Now, this is occurring point by point. So, but if I want to abbreviate it, I write this quantity right here. So what do I do now? I have to add up all the contributions. I have to add up the contributions of all of these squares and all of these sort of bent parallelograms. So the approximation of the surface area is given by what? Okay, so SA is approximately equal to, well, I have two sums. I have to sum over the vertical and the horizontal axes, okay? So I'm going to have, say, TU of UM cross VL cross TV of UM VL delta U delta V. And then the L is going to go from 0 to n minus 1. And then the M is going to go from 0 to n minus 1. Okay. Oops, there's a mistake. This should be a comma. And when you make n and so you want to take n to infinity, what does that do? If you take n to infinity, it makes more and more little squares or rectangles, and so your area becomes precise in the limit, right? So when you take a look at that, and this is basically a Riemann sum of sorts, and then so the area is exactly given by an integral. The du, this guy delta u delta v turn into du dv, and then we're integrating the u from a to b and the v from c to d. So that's pretty much why this formula works. We'll do a few additional exercises. Let's find the surface area of a sphere. So find the surface area of the sphere of radius a. Now, from geometry, I know my answer is 4 pi a squared, but I may not know why. So let's compute. Remember that a sphere is given by spherical coordinates. There are, for a sphere, two coordinates. There's the parameters theta and phi. Theta measures how far you go along the x-axis, xy plane. And then theta is how much you drop from the North Pole. So theta is this angle right here. Oops, phi. Phi drops. And the parametrization is a cosine theta sine phi, a sine theta sine phi, and then lastly, a cosine phi. And this t is, well, theta goes from 0 to 2 pi, and phi goes from 0 to pi. So that's the parametrization of a sphere. Now, to take tu cross tv, I mean, we can do it, but it's really, really painful. T theta is minus a sine theta sine phi A cosine theta sine phi, A cosine, and then the last term is 0, right? There's no thetas in the last coordinate. And then T phi is equal to A cosine phi, A cosine theta cosine phi, A sine theta cosine phi, and then here is minus A sine phi. Now, I mean, nobody wants to take the cross product of that, right? But if you do, and maybe you will, then recall in spherical coordinates, there was a volume element, dv, which was equal to rho square sine phi, d rho d theta d phi. But here, right, for a sphere, my radius doesn't change. My radius is a constant a. So the rho, which represents the radius, is now a constant, right? So here, okay, what you're going to find is that after calculating the cross product and then calculating the norm of the cross product, okay, right, this is going to be equal to a squared sine phi, okay, after tedious computation. I mean, it will take like 15 minutes or 10 minutes. It doesn't take that long, but it's not really nice. So what's my surface area? It's the double integral of a squared sine phi d theta d phi. Theta goes from 0 to 2 pi, and phi goes from 0 to pi. There are no thetas, so the integral is just 2 pi, and then I have an a squared. Now, it might be a good idea just to memorize that this integral is equal to 2. Okay, so when you're taking an exam and you don't have much time left, it might be useful just to know that fact. If you really want to integrate, I have a negative cosine phi from 0 to pi, and this gives me a 1 plus 1, so I get a 4 pi a squared. Right. So let me write down a few other types of surfaces. Sometimes a surface is just given by z equals f of xy. So these are surfaces, right, that is defined as a function of xy. And what happens here is that there's some region D, right, down here, and you're essentially interested in looking for the surface area of the surface, okay, above D. So let me describe how to find my integrand, right? So here, what I'm going to do is, it's what I call the easy parametrization, right? So in this case, the x value is just u, and the y value is just v, right? So I have t, the parametrization is t of uv equals uv and then f of uv. I mean, you can write x, y, f of x, y. That's also okay, right? But I like to use u's and v's. So that's the parameterization. And so what is tu? It's 1, 0, f sub u. Tv is 0, 1, f sub v. So tu cross tv is equal to, oops, I guess we should take the unnormed cross product first. So I get an ijk 1, 0, f sub u, 0, 1, f sub v. So this comes out to be, let's see, a minus f sub u, a minus f sub v, and then a 1. So tu cross tv is equal to the square root of f sub u squared plus f sub v squared plus 1, right? So that's the integrand. So for example, I can say, um, let let's make life not so terrible. Z equals, let's say, 3u 3x. Let me see. F of x y equals 3x plus 2y. All right, so this is a plane. So essentially what we're doing is we have a plane, okay? Find the surface area of the region above, say, 0, 1 cross 0, 2. So I have a square of a rectangle in the xy plane, and I'm going to look at the corresponding piece up here, which is tilted, and I need to find the surface area of that. So here, if I remember that recall that x is equal to u and y is equal to v. So tu cross tv is a square root of, fx squared plus fy squared plus 1, right? Well, fx is just 3 and fy is just 2. So I get 9 plus 4 plus 1, which is a root 10. So my surface area is just the integral from x goes from 0 to 1, y goes from 0 to 2. Okay, my integrand is root 10. You can say du dv or dx dy. There are no x's and y's in the integrand. So I just get 2 times 1 times root 10. So I get 2 root 10. Let's do this other example. Let's see, what number am I on? I'm on 6. Recall that in calculus, you had the following idea. You had an a to b, and you had a function. And what you want to do is you want to revolve it, okay, right? And you form a solid, and then you want to find the volume of that solid. So this is called a solid of revolution. And in calculus, we learn how to compute volumes of these things using the disk method or the washer method or the shell method or some other method, right? So this is called the surface. So let f be a function from a, b to r. Then we revolve f around the x-axis. We revolve x around the x-axis, and then the washer, the shell, the disk method, this methods can compute, right, volume. But what about surface area? What about surface area of a of something by revolution? All right, let's think about how we would do this. Now, let's just sort of change our coordinates a tiny bit, right? Let's say this is the x coordinate just because we drew it like that. Here's the y coordinate, here's the z coordinate. Now, what I'm going to have here is one parameter goes from a to b, and the other one kind of goes around this circle. So there's a theta involved. So I'm going to consider the following: t of ab cross 0 to 2 pi to R3, and then t of uv. All right, let's think about this for a second. So the x coordinate just goes from a to b. right? So that is just some u. Now, what about this piece right here? Maybe I should, instead of calling it v, maybe I should call it theta, just to remind ourselves that it's an angle. So what's going on here? Okay, notice that this height from x to y, right over here, that guy is, well, maybe it's better if I change coordinates just slightly, just to make the picture a little bit easier to see. Suppose I did the following. Suppose I exchange y and z, right? Oops. So here's y and here's z. And this guy right here, this height, that guy is f of x, or f of u. And so there's a circle here of radius f of u. So this guy right here, which I'll put over here, this guy is a circle of radius f of u, and then the theta will bring it around. So I have f of u cosine theta, and then f of u sine theta. Right, now let's take tu. Tu is 1 f prime of u cosine theta, f prime of u sine theta. Tv, or actually t theta, right? What is t theta, right? The first coordinate is a 0. And then I have negative f of u sine theta, and then f of u cosine theta. Let's compute the cross product. Tu cross t theta is ijk 1 f prime of u cosine theta, f prime of u sine theta. Oops, I should have written u, not v. Okay. 0 minus f of u sine of theta minus f of, positive f of u cosine theta. When I take the cross product, the I coordinate gives me what? An f prime of u, f of u cosine square theta plus f prime of u, f of u sine square theta. Okay. Now the j coordinate is going to give me a minus f of u cosine theta, and the k coordinate is going to give me a minus f of u sine theta. Now, take a look at this piece right here. Notice that I can factor out an f prime of u, f of u, leaving a cosine square plus sine square, which is 1. So this becomes f prime of u, f of u, comma, negative f of u cosine theta, and then negative f of u sine theta. So our next, every piece has an f of u in it, and then I'm going to square all the terms and then add them together. Tu cross t theta in norm is going to be the square root of f prime of u squared, f of u squared, plus f of u squared cosine square theta, plus f of u squared times sine square theta. So first of all, I can factor out an f of u squared out of everything, leaving me with an f prime of u squared plus cosine square theta plus sine square theta. And then I can bring out the f of u squared. Now I have to be very careful. The square root of f of u squared has an absolute value. And then I get f prime of u squared plus 1. So my surface area is equal to 0 to 2 pi and a to b of the absolute value of f of u, f prime of u squared plus 1. And then I have d u d theta. Now notice that there are no thetas in my integrand, so that just pops out here. So I have a very hacked formula. Well, not super compact, but works out. All right, let's just do one example, right? Use this formula to find the surface area of a cone of radius r and height h. Now, let's take a look at uh, what this is going to look like, surface area. Now, imagine us doing the following, right? So what I'm going to do is I'm going to tilt the cone so that it's on its side, sort of. So I'm going to think about the cone in the following way. So what I'm going to do, let's say here's X, here's Y, here's Z. I'm going to consider a line, and I'm going to revolve this line around the x-axis, and so I build a cone like that. Now, the question is, what is what is the equation of that line? Well, the height here is the radius, and then here is h. So the slope here is r over h. So this is y equals r over hx. And we can use the formula above to compute it. So I have f of u equals r over h u. So the surface area is going to be 0 to 2 pi, okay, 0 to h, because that's how much x goes. And then the absolute value of f of u, everything is positive. And then I have f prime of u, which is just r over h squared plus 1. Oh, by the way, I should have just put the 2 pi out here. And this is just du. Now notice that everything here is a constant except for the u. So let's just pull everything out. Square root of r squared over h squared plus 1. Right, and then I'm integrating u squared over 2 from h to 0. So this gives me a 2 pi r over h square root of r squared over h squared plus 1. Okay. R squared over h squared plus 1 times h squared over 2. Now I'm going to cancel that 2 with that 2. This h, I'm going to multiply this guy into the square root. And so what I'll get an h squared once it goes in. So this will become r squared plus h squared. And um, let's see, r squared plus h squared. And sorry, what I said was not quite right. I don't want to multiply the h in there. The h is on the denominator, not the numerator. So let's rewrite the guy on the inside. Right, so over h times the square root of r squared plus h squared over h squared times h squared over, now my 2's are gone, right? So I just have an h squared. So here, there's an h here and there's an h here that cancels with that h squared. So what I have left is pi r square root of r squared plus h squared. So that is the surface area of the cone. Now, it's only the side of the cone, right? So if I have a cone here, it's only this part of the cone. It's not that part. If you want to add that part, that's another, pi r squared. All right, so on the next lecture, we'll do surface integrals of type 1, which is a generalization of surface integrals, a surface area. And that concludes this lecture.